Okay, let's talk about the mole. The mole. So a mole is an amount of substance. Along the same lines as things like a dozen or a gross. Okay, so it's an amount. And where does it come from? Well, that's kind of interesting, I guess. So it turns out that in chemical reactions, you get this interesting relationship where, let's say that you have a chamber of H2, a chamber of O2, you mix them together, okay, and you apply a little heat, get some flame, okay, out the other end, you're going to get some droplets of water, okay. And it turns out that volume-wise, as long as everything else stays the same, you know, pressure, temp, etc., you will always use 2 times the amount of H2 gas as O2 gas. Or, I'm sorry, that's not quite right. Let's be a little simpler. Let's call it O. Let's call it H. Okay, there. Okay, so you're always going to use twice as much in volume of H as you do O. And it turns out that what you're making here is H2O. So what that means is, if you were to split these apart, you're always going to get 2 times the volume of H as you do O at a given temperature and pressure. So this set off some light bulbs with scientists way back when, who realized that, you know, in the early days of atomic theory, that what that probably means is, seeing as how you have twice as many hydrogen atoms as you do oxygen atoms, and it also takes up twice the volume, there's probably some relationship between the number of particles and the volume of a gas, regardless of what gas you're talking about. And this wouldn't have just been noticed with water, but all other types of gases turning into other substances or chemical reactions. And so the theory came out that a given volume of gas at a given temp and pressure contains a set number of particles. So where are we today from this? Well, what we know probably from studies in chemistry class is that if we take a chamber, we make it 22.4 cubic decimeters, which is 22.4 liters. In chemistry, they probably talk about liters more, but what you will find is that at STP, so standard temperature and pressure, which are 0 degrees Celsius, which is 273.15 Kelvin, and pressure, which used to be 101.3, but now I believe they've just changed it to 1 atmosphere or 100 kilopascals. Remember what this actually is 100,000 newtons per meter squared. Okay. At these conditions, 22.4 cubic decimeters will contain exactly what? Just been informed that the change to 100 changed this to 22.7. Gotcha, that makes sense, right? That it would have to change too. Okay, there we go. Thank you for that. And so what we say then is that any gas that's acting ideally will have 6.02 times 10 to the 23 particles in there. I used to know exactly how they calculated this number, but I totally forget now. Can't remember exactly how it was done. I think like electrical deposition of atoms onto metal, but I can't exactly remember. Now the question is, how is it that something like N2 versus something like helium, right? Here's this like kind of like big diatomic molecule, and here's this little wee, noble gas. How is it that under these conditions, if this is pure N2 or if it's pure He, we can know that in either case there's going to be this number of particles? How can that be true? And the answer is that this is not really an accurate picture of the relationship between the sizes of these things, okay? At least compared to the amount of space that we're occupying here, all right? It turns out that the size of these particles, regardless of which ones you're looking at, even super heavy gases like, say, radon or something like that, although they do have bigger atoms, the volume that those atoms occupy compared to 22.7 cubic decimeters is negligible. So they act negligible. I don't know if that's how you spell that. They act like points. Okay, a point actually takes up like zero space, like a mathematical point. So it doesn't matter which gas you're talking about now. All right. They take up the same space relative to the volume that you have here. So this this number, this 6.02 times 10 to the 23 number, this is called Avogadro's number, because I believe he was the guy who originally hypothesized this concept, and it turned out that this value here, this Avogadro's number, is the number or value in a mole of substance. Okay, and I guess technically you could say like a mole of money or something like that, although good luck with that. Okay, so now if we go back to our chamber of gas, we can think about some relationships that are going to happen. So if we put a piston on top, and this piston can move up and down, and we take the temperature of this container, and if you remember, the temperature is a reading of the average EK of particles inside of it. Okay, and we also put a pressure gauge on here. Okay, that shows pressure up and down, and we can move this plunger up and down. Okay, what we'll find is if we push down on here, we apply a force times the distance. That equals work, right? We're doing work on this substance, okay? And as I do work on this substance, two things are going to happen. The temperature will tend to rise, and the pressure will tend to go up, okay? The pressure goes up because if you have the same number of particles in a smaller space, their collisions with the walls will be higher, and that will read as a higher pressure. The temperature will go up because the average kinetic energy of particles will go up, because as this moves in, when particles collide with it, they will bounce off with a higher velocity than they went in at, okay? And in terms of conservation of energy, you did work, and there's a conservation rule there, so that work has to manifest itself, and it does so as adding heat. Okay, adding heat into the system. So heat is work, right? And I can work to add heat by pushing down. And then if I let go, this system would work backwards to push the plunger back out, during which pressure would drop and temperature would drop. Okay, as it worked back out, because particles going in would leave some of their energy to push this plunger back out. Okay, so there in kind of a nutshell is a way to think about all the gas laws. So you could say this: as temperature increases, pressure increases. Okay, as volume decreases, pressure increases, or as pressure increases, volume decreases. And as volume decreases, temperature increases. So we have these relationships here, as explained just by this. And then eventually from this, and these are different laws, like Charles's law, I think is this one. No, sorry, this is Boyle's law. No, this is Boyle's law. This is Charles's law, I think. And then there's the other guy's law. Yeah. Do you remember his name? Yeah, anyway, it doesn't matter. Oh, Lassac. That's right, Guy Lassac. Okay, then from that we get this rule. Okay, or another way to put it, kind of a more physicsy way to put it, is this. Okay, this you probably haven't seen before. So in chemistry, you would use this. Um, this R is the gas constant, universal gas constant. Okay, and it is 8.314. Okay, so there's that mole we were talking about. This is your temperature in Kelvin. This is your number of moles. Okay, there's pressure in kPa's. And here's volume in either liters or cubic decimeters, as the case may be. Okay. This is another version of this relationship. This is pressure in kPa. This is volume, again, in cubic decimeters. This is the number of molecules. This is something called the Boltzmann constant. And this is Kelvin temperature. Okay. The Boltzmann constant, this is from the same person that came up with the Boltzmann curve, and there's a relationship between R and K. This is number of moles times the gas constant, and this is number of molecules times the Boltzmann constant. Then R and K should be related to one another, okay? And it turns out this. K can be found by taking R and dividing by Avogadro's number. Okay, so they're essentially talking about the same thing, but they're looking at it in different ways. This is looking at it in terms of number of moles. This is looking at it in terms of number of particles, absolute number of particles. Okay. And so that leaves us with a value for K of